The first trend that I think is most pertinent to the work that we're doing in terms of AI are these so-called scaling laws. And the problem that we're starting to see now is, on one hand, it's sort of clear that these scaling laws are likely to continue for at least the next few years. And very soon we'll hit this sort of threshold of gigawatt training runs, which is like a previously unimaginable amount of energy consumption. We need to start to think about how some potentially different, radically new ideas for getting more compute and continuing to scale these models that go beyond the kinds of techniques we've been using so far today. So CN 101 is our first proof of principle of some of these different ideas, which comprise the way we think about building a thermodynamic processor.
Stochastic computing, instead of trying to be a tightly controlled, rigid, deterministic process, harnesses the inherent noise in the silicon chips that we're normally trying our best to suppress. And that suppression is where a lot of the power cost comes from. We just work with the randomness of the design, and that gives us an ability to not be so power dense and not consume so much power, so that we can avoid hitting these maximum temperature limits, and therefore we're way backed off from the power density. The computing approach we've chosen to implement this is a stochastic, noisy process, and the types of AI that we're looking at are themselves stochastic, noisy processes. There are fundamental limits to how much heat the silicon can tolerate before it starts breaking. When you buy an AI accelerator, for example, now, it'll have an advertised maximum throughput. You very rarely hit that maximum throughput, because if you try to run the device at that maximum speed, it would just overheat. So you have to turn the device down effectively, throttle in.
Aria's core mission is to fund scientific and technical breakthroughs that could either create or shift entire industries. So think of things like the internet or GPS or the COVID vaccine. These are the types of kind of world-changing outcomes that Aria seeks to fund. I think the key thing to do is to orient around massively impactful, what we like to call big if true ideas. So if it does pan out, it would have a big impact. And do we know if it's going to pan out? Usually no. And when you look at the landscape of advanced computing, most of the work is oriented towards the next 2x improvement. If this idea were to materialize, and if it were to scale up, would it be 2x or would it be 1,000x in terms of the type of impact it would have relative to the existing technologies that we have today? And obviously we want to orient ourselves to the latter.
The normal project sits right in this sweet spot of what we try and fund. It's extremely technically challenging, but if it were to be true, the unlock would be huge. We're talking about the much larger paradigm-shifting improvement in performance and energy efficiency.
That comes with inherently a lot of technical risk, right? Most of the ideas that could presumably lead to 1,000x gain in anything have a very high likelihood of leading to 0x gains. And one of the nice things about doing this at Aria is that we don't need to shy away from those types of ideas. Normal computing had one of these ideas that I think fits into this category, where if you look at it on its face, it seems like a very compelling idea. The concept of using nature or physics in and of itself to perform some non-trivial computation.
But the fact that this C101 chip works is something that we're extremely excited about. When we first viewed the initial Brilliant results, I think the immediate feeling was excitement. We didn't know if this was going to work or not because of the nature of what Normal have done here. And the fact that they were able to put some results in front of us was incredibly exciting.
The founders founded the company knowing that there was something there that they could explore. Patrick and his team worked on an initial large-scale implementation in discrete electronic components, proved the theory out that yes, you could compute real solutions to real problems using thermodynamic computing. And then from there they went on and brought the silicon team on board to turn it into a silicon chip.
Chips are my bread and butter, so seeing the chip wake up and work, it's a magical moment.
This particular chip, it was being brought up by one of our colleagues in LA, and he was looking at it 8 o'clock my time in the UK, and I knew he was doing this, and I couldn't bear to find out that it didn't work, so I muted my notifications until the following morning. Following morning, I see that he's producing data out of the chip, and that was a massive moment.
And I think there's a very real chance that if we are able to scale this paradigm, we will look back at Siena 101 as a legitimately historic milestone, in the sense of being, the first time that we've broken from that course of, scaling these conventional architectures. We look at it as a certain kind of moon landing.
I think this is one of the fundamental things about thermodynamic computing that makes it interesting. This is the way that thermodynamics kind of models the world, is that when you go down to a small enough level, everything behaves randomly because it's in contact with some larger environment system that we can't characterize completely. That doesn't mean that we can't predictably solve a problem.
The basic theory of this was actually worked out back in the 50s by von Neumann, one of the founding figures of computing. And he worked out the basic theory and said you could actually do that. You can have a computer with unreliable switches and it still works. What happened historically was transistors became so incredibly reliable that we didn't need to worry about error correcting for the most part. We're leaving that regime now as transistors continue to get more energy efficient. The amount of energy they dissipate becomes so small, it becomes difficult to keep them to be completely reliable anymore. So we get this regime where the computations themselves end up getting a little error prone. But nonetheless, you can error correct on those calculations as long as the errors aren't too great and get reliable answers out the far end.
When we zoom out and look at what happens on the long time scale when we're using our hardware to, say, solve a linear system of equations, we can predict confidently how long it will take to solve a problem and how long it will take the answer to converge. What changes is how many flops we can do per joule of energy. So if that can be improved by a factor of say 10, 100, 1,000, that gives you similar factors in the number of flops that you can compute. And because of results like AI scaling laws, those increases in the order of magnitude of compute give us predictable decreases in the loss of our models, which then translates to more intelligence, more useful applications, better models.
I think AI is definitely a very important set of applications when we think about thermodynamic computing and scaling these, post-autoregressive models, scaling very large diffusion models, getting to the point of, real-time video generation as a target that we think we can achieve in the next couple of years from our roadmap.
What thermodynamic computing is going to allow us to do is to build computers that are not entirely deterministic at the smallest level, but which are far more energy efficient, which is similar to the way that systems we find in nature are, that at the smallest level, they're not entirely deterministic. We can predict their large-scale macroscopic behaviors. And so I think that taking some inspiration from nature there, we're going to be able to use thermodynamic computing to improve energy efficiency and enable the next several orders of magnitude in AI scaling.
There is this other kind of set of algorithms which we could put under, physics-inspired algorithms, where folks have been using similar kinds of stochastic differential equation based algorithms or simulations for solving very hard problems in the physical world. So different areas like in drug discovery and medicine, and material science. So there's many different companies and efforts now to discover radically better materials for solving hard problems in energy, and also building new kinds of semiconductors and so on and so forth. These really hard problems rely on scaling similarly huge scientific simulations in a way that we still don't necessarily know how to do. And so we see this new paradigm as an opportunity to make that feasible as well. So basically what we're working backwards from is a 2028 milestone of having production silicon. This is something that we are kind of working very closely with a similar set of partners here to scale to the applications that we were talking about previously. And so that's really kind of the primary goal that we're working towards right now. But what we see beyond the horizon of that first production silicon is 10 years of continuing to scale a broader portfolio of custom silicon and kind of production ASICs based off this new paradigm of thermodynamic computing.
I think the future of compute is lots of different chips doing lots of different things that they're specifically designed to do. And I think our chip is specifically designed to do diffusion and thermodynamics, and I think it will be in the future the best thing for that.
But we do know that the existing paradigm that everyone uses is kind of running out of steam. We do know that the difference between the artificial intelligence systems that we use every day and the one we have in our bodies have vastly different power profiles. We have these kind of existence proofs that there should be a different way of doing things. And so when we saw their kind of thesis, it made sense to explore it. In terms of first steps, this is a fantastic first step. And from that standpoint, I was super excited. I think Normal's kind of leading the charge in this way, which is great.